Hello and welcome to today's seminar in the Smart Mobility Connection series. My name is Carly Benhart-Kukula and I am the 2019 Traffic 21 Women in Transportation Fellow. The Smart Mobility Connection series is sponsored by the Traffic 21 Institute and the Mobility 21 University Transportation Center as an opportunity for faculty to showcase their current transportation projects. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note this session is being recorded, and all participants' microphones are muted. To ask a question, please send a message through the chat box. You do not need to wait until the end of the presentation to send your questions. Now I would like to introduce today's speaker, Peter Zhang. Peter's main area of interest is in operations research, focusing on robustness, security, and fairness in transportation, logistics, and network-related problems. He received his Bachelor of Applied Science in Engineering Science and Master of Applied Science from the University of Toronto, and his Ph.D. in Engineering Systems from the Massachusetts Institute of Technology. Please help me welcome Peter as he tells us about his University Transportation Center project, Gaps and Opportunities in School Bus Transportation.
Thank you very much for the introduction. Let me just take a minute to start sharing my slides here. All right, so hope everybody can see the slides here. If not, please let me know. So I'm Peter again, and for those who don't know me, I joined CMU last year as an assistant professor at Hines College, as well as with courtesy appointment at Civil and Environmental Engineering. Okay. And this project has been an ongoing work with my colleagues and students at CMU, and with the support of UTC Mobility 21, and with also collaboration with Allies for Children, looking at the problem of understanding and trying to help with student transportation within the Allegheny County here. And so this is not a solved problem, and we are very much looking to hear your comments and suggestions, especially if this could be a way to excite any kind of collaboration or dialogue. Even without us in the loop, I think this would be a great outcome from me giving this talk here. Okay, and again, thank you very much for being here on a Friday noon during lunchtime, or I don't know, Friday midnight, depending on where you are. Let me start by a non-technical side of the question. So I did not grow up in the US. All the experiences I had with school buses or yellow buses was from movies. And this was a movie from, I think Forrest Gump was from the 90s. And then the scene or the story was basically more than half a century ago from now. All the things I remembered from this movie was how enduring there were so many different facets of American stories. And it's impressive how the director and the screenwriter can put so many different aspects within a single movie like this, stringing everything together. And as a student in China, when I was learning English, this was one of the movies that I watched and listened to over and over again on a cassette. So at that time we had Walkman where we used to listen to cassette, and the Walkmans you can switch to radio versus cassette. So that was a nice, good experience learning about all different aspects. And so why do I talk about this? So the point is it's the school buses, the yellow buses, haven't really changed much from, at least from outside. looking at the appearances, aesthetics, which is a good thing for stability, safety issues. These buses are extremely safe. The first time I rode any bus, yellow bus, was when I in high school in Canada. And the first time I got on the bus, I was like, oh, these seats are so uncomfortable. Then I realized, oh, it's a design method to keep the kids safe without safety belts. And this hasn't changed, which is a good thing. So these buses are really durable. But more things haven't changed. It's not just the buses themselves. So there's another, so we move forward 20 years. So this is a paper published in 1997, a computerized approach to the New York City school bus routing problem, and co-authored by my PhD advisor. And actually later on, he designed he and his colleagues came up with software for school bus transportation and turned that into a company. And the company was sold, I think, to iLog, and iLog was sold to IBM, and eventually he made a good fortune out of it. But that was more than 20 years ago. And so when I first started hearing about these different questions and research problems, and also people complaining about school bus systems, I was slightly puzzled by the fact that, first of all, the system has been around for a long time, and secondly, there has been research attention and practical, problem-solving attention on this for quite a while. And there's been an evidence of that. But yet it is still not solved whole. And by not solved, I mean still there are major efforts being invested and called to go into this kind of solution or problems. In particular, this is I'm just showing the banner of a transportation challenge from just a few years ago in Boston. So Boston Public Schools announced a request for a proposal, a request for solutions for solving their routing and school bell time scheduling problem altogether. And this is only a few years ago. And this background story is going to be something that shows up again in a few slides. But basically, what I'm trying to say is that these kind of issues within school bus routing and school bus management and transportation in general, or in a way, at least to me, surprisingly unsolved. So I'm new to this problem. I was new to this problem. So naturally, what I set out to do was to understand, first of all, why this is an unsolved problem. Why there's still big challenges like the Boston Public School Transportation Challenge, calling for efforts to invest into this. And we'll talk about what happened for this transportation challenge in a few slides as well. So that leads to what I wanted to talk about today. So the outline is really, on a high level, really simple. So I just feel like I am a student here trying to learn what is the actual, what are the underlying issues here? What are the tensions? What are the trade-offs? What are the challenges that people haven't been able to fully resolve this problem? And again, so this is a very simple outline. We're going to talk about challenges in this problem that I discovered, as well as opportunities that arose from these challenges. But I should say probably mostly more challenges than solutions at this point, which may be a good thing for research. And okay, so let me just give you some background on this. It's a very high level illustration. This may not be exactly the angle that can say a lot, but this is something, at least something that impressed me. So so we're looking at the sizes of different transportation systems in the US. So the first column is the number of yellow buses in the whole country. And the second one is the number of transit vehicles, public transit vehicles, including buses. And the third column is the number of coaches in the US. And then the third one, number of commercial airlines. And the last one, a number of rail cars. And what surprised me was that the school bus or yellow bus system is the largest mass transit system in the US by a lot. So this immediately talks to the fact that this is, if there's any unresolved efficiency issues, and fairness issues, and cost issues, we know the scale is not very small. And not only the number of school buses, but the number of passengers, of course, in this case, students, it's large. So we'll have 25 million students transported on a daily basis. And because of the requirement of transportation and then the rising fuel cost, etc., the cost of transporting these students is about between $1,000 and $2,000 per year for every student. And on a percentage case, in Boston, this transportation cost accounted for about 11% of school district's budget in the fiscal year 2016. So overall, this is not only is this a problem that we haven't really addressed fully, but also this is potentially a good place to look into because of the potential cost savings. And so without giving you too much, without further ado, so these are the challenges that I discovered in the school bus transportation system. It's not really an exhaustive list, but some of the things that I think to dissect and understand it in a cleaner way. So I say the first challenge that I would face is the temporal challenge. And it's really a temporal challenge with many stakeholders. And by this, I mean there are schools, there are parents and students, and there are drivers, and probably cities and government agencies as well here. But mainly we have to, whenever we design or someone designs a school bus transportation system, we have to care about, of course, the bell times, because these would dictate times that buses should drop off or pick up students to and from schools. And then the bell times would also, on the other hand, affect the schedules, class schedules, and activity schedules for the students and teachers. And for the bus run times, this would dictate parents' schedules, not only their schedule to drop off and pick up their kids, but also their work schedule. And also not only the time points, but also time windows for them to be waiting for the buses. And then on the other hand, there's also run schedule. So run schedule in terms of how drivers are scheduled to perform certain runs. Do we have a lot of drivers that do a lot of runs at the same time? Or do we have fewer number of drivers to do staggered runs over time? And so I'm going to illustrate what we mean by trade-offs here. But just to first to highlight here, there's a temporal challenge, which is something that we can't really fully satisfy for everyone's purpose. We only can talk about trade-offs. And then there's the spatial challenge, that's what I call it, where students can sometimes attend schools very far away from home, for example, with charter schools. And because of the policy mandate that school districts have to, for example, transport students within their district to any school within the 10-mile boundary of their district, then the transportation burden is not very light for a case where there's a substantial number of students attending schools outside of the boundary. Okay. And also there's in many cases a lack of efficient outside option. In this case, for example, public transit for cities that don't have a sizable or flexible bus and subway transit system. And so coupled with these operational challenges, there's a challenge financial cost from rising cost in fuel, maintenance, the buses are getting old, and it's hard to replace them, etc. So that's a huge concern for many cities. And also the new concern about health and safety during the times and after the times of COVID. So I'm not exhaustively listing all the challenges. And if you have new ideas or other perspectives, I welcome them today and also offline. But these are the things, especially the top two, are the things I'm gonna maybe go into more details about. Okay. So let me first talk about the temporal challenge here, or the trade-off between different stakeholders. And I start with a very simple thought experiment. So let's say that we have one school and we're thinking, how do we design bell times? And we have two options, two extreme options. One option is that we set the bell times to be the same for everyone, for all grades, for all students. And the other extreme option is that we do a staggered bell times for different grades. It's 8:30, 9:30, and maybe 7:30. And so this would, so these two options would have different implications for different parties and different facets of this problem. For example, let's say for class scheduling, for some reason, it's easier for school to schedule everything within the same, I don't know, 6-7 hour block of time during the day, right? And that probably the same bell time probably is good for class scheduling. And maybe it's also, so in terms of planning for parents, maybe the same bell times for parents is good because maybe they have multiple kids going to the same school or a few schools nearby, and they would like to drop off their kids either to bus stops or to schools at the same time without making multiple runs. And on the other hand, if we talk about driver scheduling, then maybe staggered bell times would be better. And that's because if we have the same bell times together, then we just have a large instantaneous demand and transportation demand within, let's say, within an hour. And if we need 20 buses to run for that hour, we can't have one driver to satisfy all the runs. We need to have 10, 20 buses and drivers. So for each driver, they're only, I don't know, making 1 or 2 shifts per day or 1 or 2 hours of work, and then they don't have any work to do. Whereas if we have staggered bell times, then maybe we can have 1 bus driver to cover 3-4 runs. That would give them a reasonable shift length. And also for other people, reduce for the planning committee, reduce the number of drivers to manage. So this is the same for vehicle demand in the sense that if we have all the drivers, all the students requiring transportation at the same time, then the number of vehicles that we need to have is pretty large. If we have staggered bell times, then of course we can have fewer vehicles to just satisfy these demand patterns sequentially. So this is a very stylized, simple example. But to illustrate, there's a fundamental challenge, fundamental trade-off between many different aspects of the problem. I'm not even listing out all the different facets here. Okay. And so, okay, so to be a little bit more specific and realistic, I'm taking this long quote from the Boston Public School Transportation Challenge. So let me just quickly read it with you, especially the highlighted area. So basically, the Boston Public School system, they have 3 different morning start times, 7:30, 8:30, and 9:30. And these bell times historically are imbalanced in the sense that more buses were serving schools at 8:30 and fewer buses serving schools at 7:30 and 9:30. And so the hope for Boston was that they wanted to have more evenly distributed bus runs among these 3 time slots, 7:30, 8:30, and 9:30. And for reasons you can imagine, as I illustrated in the previous slide, for example, better management of buses and drivers, better satisfaction for the drivers because they have a better schedule, and this is basically one of their underlying causes. And in addition, they also had a goal that they wanted to have high school students to start later, because for some reason, they found out that from health studies, high school students starting later can help them gain more sleep, function better, have better health. So there's a push to have younger kids start earlier and high school students start later. So that was the setup of the problem, of the challenge. And this is what Boston Public Schools proposed and asked people to help with. So this is basically a few numbers for the schools, for the public school system's historical performance. So they had about 600 buses, and parents' satisfaction based on a specific metric that they developed was about 48%. And the percentage of high school students that's starting late, meaning 9:30 or maybe 8:30 as well, is about 26%. And so a team of, actually many teams of analysts and transportation specialists came about to try to address this problem, try to help them use algorithms and machines to help them design better schedules, basically come up with a range of different plans. And here they're laying out 2 specific plans out of the thousands of plans here. And these 2 are special because they illustrate what are the outcomes for if we're only looking at minimizing cost versus what is the outcome if we're only looking at maximizing parents' preferences. So for the first type of design of schedules, they're trying to minimize cost as one would say a single objective optimization. And overall, they had 455 buses required, and the cost of $14.5 million, sorry, the cost of saving in $14.5 million. And the parents' satisfaction dropped from the previous one to 37%, but the number of high school students starting later increased to more than 50% here. And the other kind of design of schedules was to maximize parents' preferences, so without much regard to the cost. So the cost actually increased, and the number of buses, mostly I guess because the number of buses increased from 600 to 935, but parent satisfaction increased quite a bit. And what's more important is that the high school students starting later metric, which was one goal for them, became 100%. So that was a case where they were trying to satisfy they were trying to optimize not against the minimizing cost, but trying to maximize some kind of social welfare for parents and students. So these were two of the solutions, and then there were a bunch of solutions, thousands of solutions here. So I'm plotting out not me, but this is from a paper from the Proceedings of National Academies of Science. So the authors, they laid out these different solutions on the dots as dots within this graph. And what does this graph show? This graph is basically showing you basically some kind of cost metric, the vertical axis, the cost metric, which is a number of buses needed. versus some kind of a preference score or welfare measure from the parents and students' perspective. So as you can imagine, with a higher preference score, the better you serve the customers, potentially the more cost you would need to run the system. And that is indeed the case that we're seeing here. We have a Pareto frontier that is laying out in the way that this curve is showing. And the star here shows the solution or the existing schedule based on 2017 runs. And that was basically saying, this is basically indicating that there's a way to Pareto improve on this solution. And they're specifically also showing a few different bell time distributions for a few different solutions here. For example, the top right, this is a solution where the designers are maximizing preference and therefore not caring about cost and incurring a high cost. This would have a bell time that looks slightly more concentrated for both morning and evening schedules. And then if we look at the bottom left corner, there's a green dot here that's highlighted here, and also showing a corresponding schedule, bell time schedule for distribution for this dot, for this particular solution. This one has slightly more spread out bell time schedules. So this would, of course, spread out the bus runs, save cost, save the number of buses, have better driver schedules, but decrease preference score for parents and students. Yeah. So far so good. So this is a really nice, I think, a really nice illustration of how transportation researchers and operations research researchers can help analyze problems like this. But what was a little bit surprising, which can be a story or a good note for anyone doing research, especially at least for me, I think, is that the outcome of this research was that, yes, it was very nice. It was published in a good journal. It won prizes. And the city officials actually picked the solution, picked this design, and then one of the solutions from these thousands of Pareto optimal solutions to be implemented in Boston. But what happened was that there was a huge pushback from parents. Not that they didn't consult the parents in the beginning, because when designing the preference scores, there was I think there was a process to talk to parents and understand their preferences. But somehow the algorithm, although capturing many different perspectives, objectives, and preferences from different parties, still missed one thing. And that thing was, they didn't really understand or focus enough on how much change they're putting into the system. Meaning that in order to implement a new solution, a new set of runs, new set of schedules for the buses and the parent-student schedules, they're inevitably changing things. And this change, if not minimized, would sometimes drastically disrupt the existing routines for parents. And I'm sure if you're a parent and have kids and take buses, you probably can relate to this well. For example, if so when the solution that the school officials picked were trying to make high school students starting later by adding more high school students to start later, then of course that would bump up some other younger kids to start earlier. I'd say the younger kid used to start at 9:30 in terms of the bus rides, and now have to start at 7:30. And so from the system perspective, overall, that probably was one part of the solution that made everything better. But for parents, that was a 2-hour change in their schedule, which could mean a huge disruption to their work schedule and daily lives. And the whole thing became at least according to Boston Globe, the whole thing was not implemented, and everything was held off, and because of the pushback from parents. And so that's I think that was just a story that I think has an interesting turn of events from the start that there's a good challenge, and then there's a nice effort to try to resolve these questions from many different teams, and there were very technically sound solutions, and also engagement with the community from the start. Somehow we still missed things. So I think that's a lesson, at least for me, even though I wasn't in the project, but observing this, I think this is a good lesson to learn in terms of understanding that there's no silver bullet. Okay, so and then I'm gonna so this is basically the temporal challenge that I'm trying to illustrate here. But I'm gonna jump into the spatial one. That's gonna be a slightly different angle, but I do want to say, when I talk about the next challenge, maybe we can think about how these two are coupled. And so by spatial challenge here, I mean, for example, so this is a more local example. So what I'm showing on this figure, which is done by one of our students here on the project, is that the pin basically shows the location of the school I'm highlighting. So this is a charter school. And the areas, so all the areas highlighted are the districts where there are students that come to this school. So basically, there are a lot of different school districts that are sort of connected in a sense to this charter school. There's an online web application that we can play with this. If you're interested, I can show you later. As I mentioned, in Allegheny County, we have a 10-mile rule where the district will have to provide transportation to students attending schools within 10 miles radius from the district's border. And that pretty much adds, on average, 2 to 5 extra districts for any particular district to serve. And for example, in one Salisbury Township school district, they have 2 schools within the district. But then they have to bus students to 46 different schools because of the rule. And there are similar rules in other counties in the US, not a unique event here. And there have been solutions, partial solutions for this kind of issues. For example, in Ohio, they have this Ohio Shared Services Collaborative, which is an association of 20 school districts. And they basically share resources based on the drop-off and pickup locations. And they also have a web-based scheduling application that makes everything easier. And in Detroit, there's the Go Line initiative. I think that's the figure on the left. Basically has some kind of a shared transportation system that goes around and helps multiple schools to transport their students. And so basically, what I'm trying to illustrate here is that there's one potential effort that people are trying around the country in order to help this kind of this coverage problem, this problem of one school in the middle having to serve many different schools far away from this this school itself. And both examples here illustrate a case of collaboration. The collaboration in terms of multiple schools, 2 or more schools, come together and say, hey, can we share our bus routes in order to transport our students either at the same time or in a staggered manner, so that we can save on the number of buses, we can save on the total transportation length, and we can save on cost. And that is one thing that we're trying to understand here, which is, can we understand what is the benefit of any type of collaboration? What is at least in the beginning, what is the transportation benefit of collaboration between any schools? And this is not a trivial task, because imagine if even if there's only 20 schools and we're choosing a subset of 3 schools to collaborate, there's going to be thousands of different coalitions to choose from. And within each coalition, if we want to quantify benefit, even just the transportation cost benefit. And even if we don't worry about time windows and this and that and solve a classical traveling salesman problem, this is still non-trivial, and solving thousands of these non-trivial problems is not really feasible for many cases, especially if we have complex or arbitrary locations and for schools and students here. So that is one thing, first thing we set out to do. So this is one small technical aspect that we identified that we can start with. And so what we do is, instead of trying to precisely calculate the benefit of collaboration, which can be done by calculating the cost of separately routing and then jointly routing. So instead of fully calculating those with full TSP solutions, we can try to use closed form approximations to approximate the benefit of collaboration. And if we can do that, if we can understand the benefit of any coalition very quickly, then we can quickly screen all the different correlations and try to understand what are the lower hanging fruits that we can try to talk to the schools, not the fruits. And then here's a classical theorem from the literature called BHH theorem. Basically, it's a way of estimating traveling salesman tour length. And then it says the following. So given n randomly drawn stops in the region with an area of size A, the optimal traveling salesman tour length is proportional to square root of n times A. And so basically we're saying that given input, which is the number of stops and area size, we know that the tour length is pretty much proportional to square root of n times A. And this proportion, this constant, this coefficient k, basically when calculate the length of k times square root of n times A, this k is fixed. Fixed regardless of the area size and regardless of the number of stops. So this is nice. So this gives us some way to start. It gives some kind of leverage to understand, to basically calculate this very fast. And the intuition behind the square root is basically, well, if we're routing things around for example, a square, then a reference length could be the side length of the square, which is square root of A. And then similarly about the number of stops. So our plan is to say, first of all, let's estimate the coefficient. This has been done in literature, but we wanted to do it again ourselves and then try to get more insights. And then also improve the structure model of k times square root of n A, and then extend this analysis to multiple schools. So this BHH theorem here is just talking about estimating the tour length of just a set of points that you have to route together with the same starting and ending point. But when we talk about multiple schools in a coalition, we have to worry about the sequence of picking up students and dropping off students, as well as transporting between the schools. So there's additional complexity coming into this transportation problem. And so first of all, let me say we're verifying and estimating the coefficient k. And how do we do that? So basically just randomly generate big N samples in a region with fixed area A. Of course, we can change the area, but let's say we have a fixed area A. And for each sample, what we have is a set of n s points and sub s points in the region. And so this, you can think of this as our independent variable in this training or in this regression. And the label that we generate for this training or another kind of input data, the dependent variable, is the optimal TSP tour length connecting all these NS points and this particular set of NS points. We do this with a taboo search method, or any existing method that you can find off the shelf. So then we have a big N number of samples like this. For each sample, we have a TSP sub S and then N sub S as input. And then we basically solve this optimization problem. We find coefficient k that can best estimate the TSP tour length based on this formula k times square root of ns and a. Yeah. And notice that this looks like there's some nonlinearity in the problem because of the square root, but it's just actually a linear regression problem because the input square root ns times a is one number for every sample. So we're just basically solving a linear regression problem. K here is the coefficient that we're trying to solve. And what are the samples like? The examples of the samples are basically something like this. Or if we define an area like this, a square area like this, and then grid it, then we can just randomly draw these k samples or k stops. And so each layout here corresponds to one sample in our training model. And overall, we found that the k's are fairly consistent. So what we're showing here is basically on the horizontal axis of each figure is the value n times a square root. That shows you what is the magnitude of the problem. And then on the vertical axis, this is the optimal TSP tour length. And then the line basically, the slope of the line is basically k, or beta in this case, in the calculations. And of course, this coefficient is different for different metrics of TSP length. We can have Manhattan distance, we can have Euclidean distance for TSP. Right. So that's the start, that's the basic. Now, and then we thought about, okay, so there's still some error margin, so maybe we wanted to improve that. How do we improve the estimation? Well, one thought is that we are not using enough information here to train our estimation model. And what do I mean by that? I basically I'm only using the number of stops and a very rough estimation of the area size. What if we can do more? What if we can use more information about the specific locations or the specific layout of any set of points, and then try to understand what is the optimal traveling salesman path through them? Well, we can of course do this. One thing is we can try to use not just arbitrary square or uniform like a fixed square to contain this area, but use a layout specific area, something like this, and then use maybe the two radii to try to represent the layout of the points. Right. So now so instead of using only the number of points and then the square to represent the layout, I'm using a tighter information set or more information to represent the layout. And then in order to retrieve lambda 1 and lambda 2, we just need to go through a few technical calculations, which is basically something like where we retrieve some kind of a matrix that shows the distance between different points, and then use that matrix to do some kind of principal component analysis to get the first and second largest eigenvalues of the matrix, which correspond to lambda 1 and lambda 2, as I'm illustrating here. And the hypothesis we had was that the estimation for optimal traveling salesman problem is going to be this one coefficient k1 times square root of lambda 1 times n plus k2, another coefficient, times the square root of lambda 2 times n. So basically that's just trying to mimic what BHH theorem is saying, but adding more ingredients into this approximation. And of course we had to set out to try to estimate that, and the same procedure goes just now, but now just we have a different, more information to train. So randomly sampled many different points within the artificial synthetic data set, as well as data sets from the origin destination data in New York. So that's one way to get a more precise estimation. So we found that this new formula that we're estimating, we're trying to find the coefficients of K1 and K2. This new formula made it better. So we had about 30% improvement in fit in terms of root mean squared error. And so that's an encouraging sign. And but on the other hand, we also notice that it only takes a very few samples, a very small number of samples to train the coefficients. It's not surprising because all we're doing is a linear regression here, which is training Ks or K1 and K2s. And so that's the implication of that is that we can actually train these coefficients online. What do I mean by online? It means that we don't have to collect all the data and then figure out K1 and K2 for a specific city. But what we can do is we can actually observe realistic runs, and whenever the run times trickles in from real experiments or real runs, we can update our coefficients, and this is called online learning. And so basically, in order to simulate that process, we did online learning with querying from Google Maps. They have a way to use the API to ask Google of what is the traveling distance and time between any 2 points, for example, in Pittsburgh. Okay. And they can also incorporate, so basically they can incorporate real-time or real historical traveling or traffic data. So that's pretty much the same procedure, but now we're just doing things sequentially, not collecting all samples at the same time and training the coefficients, but doing these samples one by one. So we get one sample and we get the distance matrix from Google Maps. We calculate the matrix, the radii, and we solve the problem, TSV problem to get us the label. And then this, the important part is that we can update the coefficients K1 and K2 based on the new sample. And then we iterate until the K is stabilized. And overall, we did experiments on the map that is familiar to us. So here we have, so we're generating 5 to 50 nodes or stops within the map. And we're using this as query by Google Map API. And overall, we found that it doesn't take too many training steps, meaning that we don't need too many samples to train this data. So both the training loss and validation loss for this learning problem drops quite fast. So that's a good thing, because in reality, maybe we can then we can try to say that we can observe bus runs almost like in real time over a semester or over just a month, and get data and then use that data to train specifically our approximation scheme to understand what is the traveling distance or traveling length for picking up a set of students within the country. And this set of coefficients would be very accurate for this specific city. And so I think I'm almost running out of time, but let me just give you one last technical slide here. So this is basically saying that we also want to incorporate the actual collaboration. So previously, I only talked about naively just routing through n different stops. And now what if we want to incorporate the distance between schools in order to understand the actual cost of transportation or length of transportation for multiple schools collaborating together? Well, we have to incorporate some kind of metric to understand what is the distance between the schools. So assume that we have some kind of distance metric for schools. For example, 2 schools, we can just say the distance between them is the distance between them. And then we further extend this traveling salesman or optimal tour length approximation formula to include the distance between schools, and then we train this again, and then we realize and we arrived at the fact that our hypothesis is pretty similar to the result. So basically that gives us some hope for further future steps on this. Okay, so basically overall what I've been doing and what we have been working together with colleagues is that we're using this analytical approach as one technical tool to screen the benefit or understand the transportation cost for any arbitrary collaborations, right? Using slightly more information than the classical PhD formula. And then, so with this, we can then identify suitable subsets of schools to collaborate or routes to collaborate. And once we have those potential correlations, we can then do high fidelity analysis, right, computationally with optimization. And once we have that, then if we're convinced enough that we know theoretically, computationally, there's a sizable benefit for collaboration, then we can try to talk to people to see, hey, well, is this something that you're willing to try? And then the hope is that this whole process, this computational process, analytical process, is accurate and fast enough so that we can do this very, very quickly, and then go back and forth between schools and, for example, Allies for Children. Because usually, I think this would lead to an iterative process with multiple engagements. And the longer term outlook for this whole area is that I think there's no silver bullet. As I illustrated, there are quite a few challenges, and they're all related. I think they are, for example, the spatial challenge. If we try to solve that, if we improve on that, maybe that can help with the temporal challenge, because overall we can save time, then we have a little more flexibility in the system in order to go around. Yeah. And I talked about one potential solution of combining routes together, but maybe another idea is to divide up the routes. So not using one bus to serve all the routes, but have a bus to pick up most students in a concentrated area, but other vehicles, smaller vehicles or faster vehicles or more dedicated vehicles for accessibility purposes for students that are further away from the main cluster. And so that could be another different opposite angle to think about this. And so overall, I think, in my limited experience, I think that the procedures we should have is we should have, first of all, identify the resources. I only talked about yellow bus today mostly, but there are third-party smaller vehicles, vans or cars, Uber Kids, and these are different services that are popping up all over the country. And there's also third-party large vehicles, transportation methods, public transit. And then I think for every problem solution here, we have to try to identify the participants, like schools, parents, students, drivers, looking at all the welfare measures for each one of them. So because missing out one would mean pretty big obstacle down the road. And procedural fairness is one thing that I think is important for many cases. It's just engaging the community. And ideally, of course, if we want to have a holistic solution, we would want to engage everyone at the same time over multiple rounds, and everyone have to sit together so that we reach an agreement. But that's usually infeasible. So I think it's also good for that there's a group of people that can take the time to talk to everyone and understand people. For example, I think Allies for Children is doing a fantastic job, and we at CMU are trying to be a liaison for some part of that, and we'll love to hear your feedback. And so this is a process that we're also learning. We're trying to think about what are the potential routes, and then put together not a single technical solution, but something that's larger and that's more comprehensive. And as I said, we're developing a screening tool for combining routes, and we've also been talking to companies to understand what services they have and the potential to leverage their service in order to have a different angle to solve the problem, breaking up the routes and understanding what is a more efficient way to serve everyone. And last but not the least, I want to thank everyone involved in this project so far and in the future. So we have a funding and partnership with UTC and Mobility 21. Data is from Allegheny County public available data sources, and also comments and suggestions from Allies for Children, and collaborators, Professor Hai Wang, who is affiliated with CMU and SMU. And we have students, Zhang Li and Hao from CE, they're masters. They're fantastic students, and Neha, who is a PhD at Temporal. They've all contributed very much to this project. And thank you very much for your attention. And if we have a little bit of time, I'd love to hear any questions that we may have.
Thank you, Peter, for sharing your work. And to all of today's attendees, thank you for joining us. As I mentioned earlier, today's presentation will be posted on the Mobility 21 What's Happening page of the website, along with a link to the video of the session. This afternoon, you will be receiving an email asking you to take a short survey about today's SMC. Please take a few minutes to provide your feedback. For students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transport nerds. Our next Smart Mobility Connections will feature Carly Jo Wong discussing her UTC project, Incentivizing Taxi Movement for Balanced Citywide Services on Friday, December 4th. Watch for your invitation to join us closer to that date. Again, thanks for attending today, and please feel free to contact us with any questions.